that helps. One other announcement, we have a discount on the Berlin trip through Saturday. So if you get your deposit in by Saturday, there is a $200 discount on the Berlin trip. If you are interested, please let me know so I can get you on an email list so that you can get more information, kind of the tasks that need to get done, things about fundraising for your trip, that kind of thing. Definitely want to get your email. It doesn't commit you to anything, but again, it does help you if we get an opportunity for a discount for me to let you know, hey, there's a discount or there's something that's going on that it's time sensitive. So please let me know if you're interested. And again, the only non-refundable part of it, from what I understand, is the payment for the insurance and the deposit. But all you have to turn in to lock your price in is the deposit. So please let me know so that we can get this going. All right. So now we're going to start talking about design. Questions on the planner? Did anybody get their planner started? I got a couple got the planner started. That's good. Like I said, if you want to come by and see now I will let you know right off the bat that this planner may not be the one that's for you, and you'll find out by doing the monthly, daily, weekly. You will get a better feel for what planner does work for you. And I will tell you, it changes over time. Sometimes in your life, that daily planner is a must. Sometimes in your life, that monthly planner works just fine. Sometimes it's your weekly planner. I have to see my week at a glance. So I have a planner right now that has the daily on the weekly, so it does help, but I have to see my whole week at a glance. So, all right. Now, we have not, there we go, try that again. Let it think about it. It's not as bad in here as it has been. I think they've got the air conditioner partially working. Okay, so we're going to start talking about engineering design. One of the reasons that people want to become an engineer is they want to, invent something. Okay, and that's kind of one of the things that we think about when we want to do engineering. The others, we want to improve processes, or we want to build stuff, right? We want to build stuff. We like to tinker with things. How many of you have taken apart a motor in a toy? How many, most of you probably had more fun taking the toy apart than playing with the toy, or modifying the toy to make it do something different, or taking the motor or the servo or something out of a dead toy to make it into a missile launcher, something else that would do stuff. How many of you did robotics? Did the robotics team? How many of you did Legos? You have boxes of Legos in the attic right now? I have at my house still to this day. I probably have the big totes, not the little totes, the big totes. 5 big totes of Legos, many of which are still in their original sets put together. Needless to say, my children were a little OCD. They kept their sets together. And now the collection is expanding. So Legos, blocks, variety of different things. So we're in that process. So you guys have actually done a design process. You just never did that, and you never thought about it in terms of its steps. So this chapter actually looks at a variety of different things, but the basic process when we're going through an engineering design is we're recognizing the need for something. Now, as a kid, it's, I just want to build it, okay? But it's still recognizing a need. Now, for us as adults, right now, there's got to be an app for that, right? There's got to be an app for that. Or, gee, I really wish I had this gizmo, or I really wish that this cup would be a little different because it's not, it's not the right size, B, it has a plastic straw. You know, there's something that's driving you crazy about a particular thing. And I'll tell you one that I looked at over the summer was, and I finally found it because it didn't come under what you would expect it to be. I looked for this summer, I have a new puppy. A lot of people know that I have a new puppy. He's 6 months old. His name is Agnew. All right. It's spelled A-G-N-O-O-O for you chemistry folks. That's silver nitrate. And so he's our third silver nitrate Dalmatian. So Agnew, he's out there, and that's because freshman lab coats when I was going to school, if you spilled silver nitrate on your coat and you went outside in the sunlight, it's a photoreactive chemical, and you had black spots on your lab coat, on your nice white lab coat. So that's why they're named silver nitrate. But I was going, all right, I'm walking every day with my puppy, because if you don't, you come home to a shredded house. And so I thought, gee, I wonder how many more steps, because he's walking up and down, walking back and forth, doing all kinds of stuff. And I'm going, I wonder how many more steps he's getting than I am on my Fitbit. And I went, I wonder if there is a dog pedometer. Well, I looked up doggy pedometer. Now, I knew there was a horse pedometer out there, because I've seen those. And cross-country horseback riders use them, endurance riders use them. So I knew there was a horse pedometer. So I said, surely there's a dog pedometer. If you actually look up the search words for dog pedometer, you get nothing. Zero. Nothing shows up. And I'm going, if there isn't a doggy pedometer, there needs to be one. There really needs to be one. Because I'm thinking, I can attach my Fitbit to my doggy, right? I'm pretty sure I can do that. Turns out what it is they don't call it a pedometer for a dog. They call it a dog activity tracker. And there's actually three or four good ones out there. The one I'm using is a Fitbark. It costs about the same as a Fitbit. And I'm pretty sure it's probably the same company, because my Fitbark and my Fitbit kind of link up together. They work really well together, and it's shaped like a little doggy bone that you put on the collar. So it's a pretty cool little device. The thing I haven't figured out is your Fitbit's only good for 7 days. Your Fitbark is good for 6 months on the charge on the battery. And I'm going, well, how come I can't get my Fitbit to have that kind of a charge? So it's kind of an interesting piece. Anybody have hunting dogs? I know you do. You got hunting dogs? There is one that's based off of tile technology that is that you can actually, with an account, you can GPS track your dog. And for those that have hunting dogs, particularly coon dogs, I could see that being a must. Being able to find your coon dog afterwards and being able to GPS track your coon dog. That one's a little bit more expensive, and it does require some service associated with it. But if you've got hunting dogs, I was looking at that and going, that's just like a no-brainer, man, to be able to look at that piece. And having a coon dog, I understand trying to keep a coon dog kind of together and not running off is a little more difficult. So that's recognizing a need for a product or service. So that's one of those things that we're after. Then the other thing is, what's the problem? What's the problem definition that you're looking for? If I'm dealing with a hunting dog, I want to know where my dog is in case I have to go figure out what happened to it after it's run down and out there. So we look at, well, what's the problem I'm trying to solve? Right now, everybody's trying to solve the soda straw problem. Okay, well, there's two ways to solve that problem. One is to get the reusable straw, which is a steel straw. The other is to do the paper straws. And the paper straws, one of the reasons we went to plastic straws, is because paper straws have a tendency to disintegrate. So we've got a problem or a solution. Then there's a case of doing the research. So my initial research said, oops, there's a gap here, but I have to figure out if there's really truly a gap. All right, if there's really truly a gap. And so you got to kind of think about what that gap is in terms of optimization. You also need to make sure you do the research. So my first search terms may have led me down a path to say, okay, there isn't something there, but you had to look at other search terms. So we want to be able to look at it. So if we're doing this right now, we're doing a design project. I've assigned it to you, so there's your need. You got to design a paper airplane to meet a certain thing. We've got the problem. I either want to make it have a loop, I want it to glide farther, or I want it to stay aloft longer. So there's something that I'm trying to fix with it. Now, your research is up to you, because I know if I Google paper airplane designs on the internet, I think I'm going to get just a few hits. Because when I was growing up, I at least had a book of 1001 paper airplane designs. So that's my book that I have on a shelf, not counting what's out there in the World Wide Web, so to speak. So there's research and preparation. Then after you do that, they say that invention comes to a prepared mind. We build on those pieces of things that we've looked at. We've looked at 100 designs, and now we're trying to build it in our head as to which design is going to work best. So we're going to conceptualize it. We're going to bring all that stuff together, and usually what we do, and the step that's missing in here, is the prototype. Usually you build a prototype. Usually you do a bench research. If I'm doing a new drug formulation, if I'm trying to do an engineering design of a new drug formulation, I can probably make that drug on the bench top, and my first or third time that I do it, I may have 20 steps to the process in order to get that drug to go from its basic ingredients to the final formulation. Well, 20 steps is not going to be a good commercial process. So I have to pilot it, and then I have to start optimizing it and evaluate it. You know, do the evaluation, then optimize, and then you got to present your work. Unless you're doing trade secrets, and then you don't want to present your work, but you still got to sell it to management, so you still got to present your work. So you've got to work through each one of these steps. And then you get to do it all again, right? You get to do it all again. So according to our book, we want to recognize what it is. You know, the first person that put wheels on their shoes to make roller skates was saying, I'm trying to get someplace faster. And the need for the product can come from you, could come from your company, or somebody could come from the clients. We haven't talked about it yet, and we're going to get there. We're going to talk about the Engineer's Code of Conduct. We're going to talk a little bit about ethics. We're also going to talk a little bit about intellectual property. Who owns the right to whatever is developed? So in that case, it does come from you or the company or your client, but the agreement is going to be who's really there. Because if you're working to solve a client's problem, it's a client work product. Meaning even though you came up with it, it's still the client's. Now you may get listed on the patent if the client chooses to patent it, but who owns it is an idea of intellectual property that you have to worry about. So there's some things that go into engineering that we never really think about. Is where did the idea come from? How do you share credit? Historically, the big companies, when they did their patent ideas, it was the lead researcher that got credit. So even though his group may have 10, 12 people, and I did use the word he on purpose, because the majority of the time it was a he, way back when, not always, but the majority of the time it was a he, that person got credit no matter who was in the staff that was working on the project. So let's take one of the most famous cases, the discovery of DNA. It's also the most famous snub of the Nobels, because Watson and Crick would not have been able to formulate and prove their idea without the aid of the woman who actually did the X-ray crystallography that showed the double helix pattern and developed the double helix pattern. So Watson and Crick got credit and did not give credit to the person who actually brought the data to them. and brought it out. So it's one of the bigger snubs. And that doesn't all, and it's not just, in some cases it was definitely an oversight, but it was a cultural thing at the time that oversight was there. Big companies for many, many, many years would not recognize their technicians on their patents. Phillips Petroleum was one of the first that the technicians got the patents, not necessarily the research scientists that were working in the groups. The culture at Phillips Petroleum was such, whoever brought the idea forward was the one who got the patent. And there are several really cool patents that were held by technicians that, because they said, hey, this is going there, and I really think if we did this or we tweaked that, we would get it, and they actually got the patents for it. But it was a cultural thing that did not allow for patents. And that cultural thing also impacted the development of polypropylene and polyethylene. Polypropylene and polyethylene was invented by Phillips Petroleum over in Bartlesville. Made billion dollars in industry. But the people who won the Nobel Prize for the development of polypropylene and polyethylene, even though they did not invent it, they did not identify the catalyst, they ended up identifying the catalyst about the same time as Hogan and Banks did for polypropylene and polyethylene. But they were in academia, Hogan and Banks were in industry, they published first. United States is first to invent. Took 19 years to prove that Hogan and Banks invented polyethylene and polypropylene in numerous lawsuits down the way. Ziegler and Nada got the Nobel Prize because they were academics and they could publish. Hogan and Banks worked for a company and couldn't publish. And then it ended up in the courts to show that after they patented it, that they had invented first, but because at that point in time, Ziegler and Nada had already received the prize. So you get a lot of interesting cultural things about the intellectual property as to where the problem comes from. And I will tell you, Paul Hogan was always miffed that he did not get the prize. But he got the big prize in the end. He got the big prize in the end. A lot of dollars. But he was miffed. He's a very interesting man, Paul Hogan was. So we have to define and understand our problem. That's what is it we're trying to fix. And then the next part of it is you got to sell it. Just because you got a solution to the problem doesn't necessarily mean that it actually is going to sell. Think of the paperclip. How many different types of paper clips and configurations of paper clips are out there? I can invent a new paper clip. The question is it going to do me any good? Now, it may for a particular application, but let's take the paper clip initially. Okay, the paper clip started out, there's actually a really cool editorial in American Scientist on the invention of the paper clip. It's a pretty interesting thing. So we got the paper clip, we get the invention, and you think about what happens with the paper clip and what the different types are, different applications of the different ones, and you think, okay, if I invent a new paper clip, it's probably not going to do me any good, except what about the ones that make the really pretty fun ones that are in fun shapes, like little doggy shapes, little star shapes, and different colors? Well, okay, maybe that's something that's good because I can sell it. Doesn't necessarily change the problem any, but I can sell it. But what if I don't want that paper clip to come off anymore? That led to the invention of the staple. Okay? So you can start thinking of, well, that understanding the problem, we can even go back and look at a few fun parts. Because of that article in the paperclip, I actually looked into the patent history of the clothespin. Because most of us don't use clothespins for clothespins anymore to actually hang on clothesline, although some of us still do. But clothespins, there are actually in K County, which is the county we're in, there are 5 patents for clothespins. Now the really interesting thing is they were all submitted by men. And I still am scratching my head going, okay, not quite sure why men would be submitting things for clothespins, but All right? So you got some interesting pieces that are there. So you got to do research and preparation. You got to get as much information as we can. Can be, and this is where invention comes from that we don't necessarily think about it. Let's talk about two changes to processes. Most people have at least seen, either on TV, even if you've never flown before, you've seen the little orange cones where the guy is guiding the plane in and is flashing with the orange cones with the flashlights to stop the plane. And you're going, well, that's a simple idea. Okay, wonder where that came from. Wonder why they do that. Turns out they do that because of the Berlin airlift. That's one of the innovations from the Berlin airlift. You got to think of what's going on with the Berlin airlift. Berlin airlift is causing planes to come in like every 30 seconds. They had to be able to move those planes efficiently around the airfield and be able to get them in and unloaded very, very quickly. So one of the ways they did it was, how do you guide planes into parking spots and without them running into each other? Somebody on the flight line came up with, I can do these things and cause glowing cones so the pilots can see it no matter whether it's dark, it's light, it's whatever. That's where that innovation came from. So that's one of the inventions that came from the airlift. Now, if you go to Walmart, Lowe's, TSC, any of the big box stores, and you ask them if they've run out of something, and you say, when is the next time you're going to have it in stock? And they say, well, the truck comes in on Tuesday, but I can't guarantee that that's going to be on the truck. Because before the Berlin airlift, what you had was a truck or a wagon or a plane that was filled with flour or gasoline or crude oil or sugar or beans. Well, if I'm flying planes in once every 30 seconds and I'm worried about the enemy shooting me down, if a plane goes down that has all the flour on it, I am now totally out of flour. I'm going to have a problem. I'm going to have a shortage of one item. The other problem is the space that a bag of flour takes up is different than, say, the space of linens, clothes, bandages. It's going to take up a little different space. So the space requirements, if I have my entire plane filled with flour and I'm at a weight limit, because it's a plane, I'm at a weight limit, I've got a lot of empty space in that plane that I could have been using for something else. So now what they do is they pack the truck based on an optimization of weight and variety of products. So that if I lost one plane in the Berlin airlift, I didn't lose all of my medicine. I didn't lose all of my bandages. I only lost a handful. Well, the next plane's got a handful more, so I'm much better off. So understanding those ideas spread to other technologies and other things that we use from different industries. So looking at how somebody else solves a problem may work towards your particular industry. And we've done that a lot of different ways. You see a lot of cross-pollination of Henry Ford's assembly line didn't necessarily come from the assembly line. He got an idea about how somebody was putting something together in a different shop. McDonald's, good old McDonald's, didn't use an assembly line function in the kitchen until the 1950s, yet the assembly line had been around since the early 1900s to create efficiency in the restaurant industry. So you can go from manufacturing to some other industry as well. So you look at what other folks are doing. You want to kind of keep track of what other folks are doing. Ideas and concepts. And not everybody's an idea person. I am not an idea person. Okay? That's not me. I was also a very crap bench researcher. Okay? For one reason is I didn't like to stay on that same project. It drove me crazy. I needed other projects. I needed lots of projects. that was not my skill set. My skill set was not necessarily the ideas that are coming up. My skill set is I'd sit in a meeting with a group of folks, and they would be talking about what they were doing, and you would listen to them, and you'd go, that's kind of an interesting thought. And my brain would have it run down the railroad track with a little bit of things. And I'd go, well, I know it's not working for that, but you know, Joe over here has got a similar problem, and what you're telling me might solve Joe's problem. And they would go, well, I hadn't thought about applying it there. Well, so we go over to Joe, and sure enough, Joe says, gee, I never thought about it that way. And they would go, and it would work, and it would tweak Joe's problem. So my skill set was to be able to listen and apply it in someplace else. And that's where I didn't come up with the original idea, but because I was listening to what was going on, I could apply it to somebody else's, and I could create those cross boundaries so that other people could use it. The other thing that I would look at and be able to deal with, we had a person, if you ever read Fast Company, Fast Company is a really, really great magazine. It's looking at innovations, it's looking at technologies, there's good career sections in it. Fast Company is a really cool innovation type magazine to look at. And they interviewed a person by the name of Marvin Johnson. Marvin Johnson happened to be a mentor of mine, kind of cool individual. He retired only 3 times, I think. And he was known as Mr. Patent. At the time Fast Company interviewed him, he had over 250 patents. And Marvin has invented everything from the freeze-dried car, which is in use, by the way, which is one of the funniest stories ever. But he's also known for metals passivation and fluid catalytic cracking for refining operations. But that's just the one that made the most money. But he has numerous patents on a variety of different tweaks and things that are out there, and some crazy ones as well. But you would sit in the meeting with Marvin, and he would sit there and he would tell you about this new cool thing that he was doing, and he would say, because at the time Phillips patented everything. They also did composition of matter patents. And you'd say, well, did you turn in a patent idea on that? And he goes, well, no, everybody knows that. And we all look at him and go, Marvin, the only person that knows that is you. And we would go, I know it now that you told me, but you're really the only person that would know those kinds of things. And so those pieces of the conceptualization, he didn't necessarily recognize when he had a new idea. And it works out that you have to be everywhere. And that's where analyzing the merit of a concept becomes a really critical skill. It's a critical skill, and even the people that are known for patents may or may or not be able to do that. And then it's the planning stages. Okay? Then it's the planning stages. How are we going to do this? What's project steps that we're going to follow through on? How are we going to do it? We're going to run our models. We're going to do all the hard work part of it, and then we'll do the evaluation. So people have a variety of interesting skill sets, and there's numbers of methods for evaluating alternatives. Huge number of methods for evaluating alternatives. One is the cost of the process. One is the cost of materials. One is the cost of a variety of things. Now, let's talk about evaluating alternatives, because the book is going to get you into sustainable design. It's going to get you into sustainability and optimization. It's going to get you into a variety of different ways of evaluating. So one of the questions that you have to look at is, if I am designing for the environment, which is an engineering concept that we look at, we're looking at designing so our products are renewable, or coming from renewable sources, or are becoming the least harmful. So let's take our cell phones. Cell phones are pretty cool stuff. Well, they got some interesting dilemmas, right? Well, they're ubiquitous, is one thing. But in order for your cell phone to work, I have to use things like gallium, indium, some pretty rare elements. There's only certain places in the world that I can get those elements. But that's why my touch screen works. That's why I get the vibrant colors. That's why I get all those things that I want. And some of those elements are considered endangered, meaning that we don't know how much of it we really have, and we don't know how much that it's getting there. And we know that those, in order to get those elements, I have to do mining. And I always told my dad I worked in petroleum, he worked in mining. I said I was at least one rung above the bottom of the ladder. He was the scourge of the earth. I just was a mess. So, you sit there and you look at, when you're talking about designing for the environment, you're looking at, well, how am I going to deal with this? And I'm going to weigh those ideas. So we can go in and we can look at alternatives. So let's take a process, and I always use this one in chemistry. We have two processes that are called alkylation, that take small molecule things like methane and make them into big molecules like ethane and propane and butane. So I can take those small molecules and put them together through a process called alkylation. Well, that alkylation processes, there's two commercially available processes. One uses hydrofluoric acid, one uses sulfuric acid. And if you know anything about hydrofluoric acid is bad stuff. People don't like it. It is highly reactive. If I get it on me, I have to have special first aid. There's a whole lot of potential hazards associated with hydrofluoric acid. Sulfuric acid is still an acid, still can burn you, still can have a variety of different things that are happening associated with it, but it's considered friendlier. It's a friendlier acid. Well, in order to do the process, when I worked at the Woods Cross refinery in Salt Lake City, I was there for 4 years. We took one shipment of hydrofluoric acid. One shipment in 4 years of that particular acid, because it's used as a catalyst. So if you think about that, that means I only had to bring in one truck. Sulfuric acid, on the other hand, most refineries that use sulfuric acid as their process have to have a whole nother unit in order to produce the sulfuric acid to run the process. Otherwise, they're taking a shipment a day of sulfuric acid. So sulfuric acid is bad stuff. Hydrofluoric acid is really, really bad stuff. And I got to weigh my options here. I have to weigh my options between those two processes. The sulfuric acid process is not as efficient as the hydrofluoric acid process. And so it ultimately comes down to a weighing of, is it better to have a little bit of really, really bad stuff or a whole lot of bad stuff? That's one thing that's an alternative that you have to evaluate. And I'll say it depends. It depends on the situation. It depends on the ultimate application. It depends. So we've got those different pieces of things. It depends. So we can all go back to the clamshells versus paper for wrapping hamburgers. We get on these kicks and we don't necessarily think of the whole life cycle. And that's one of the things that when we evaluate our alternatives, we have to think of the life cycle. Biodiesel is one of those things that we have to think of the life cycle. Ethanol is one of those things we have to think of the life cycle. If I am using corn to make ethanol, I'm taking corn out of a food chain, either as animal feed or as people food, to make a fuel. Is it worth the whole life cycle piece in order to do that? Because personally, I think growing corn in the Texas Panhandle is not the best optimization of our land resources, water resources, and everything else, because corn is a highly water-intensive crop. You've got to evaluate in all the different life cycle pieces. And then you get to optimize. Which is better? How many steps? Which is more cost effective? Which is more time effective? Can I apply and this is where AI is coming in, artificial intelligence. Can I optimize things a little bit better? And looking at our systems. So optimization is kind of critical. And then you can do flow charts. Flow charts are always so much fun. You can do flow charts to actually look at it. And then you get to do the repeat and redo and all of that. But this gets us to why we have to do the communication step. You have to be able to communicate your solution. Whether it's to get the patent, whether it's to your coworkers, whether it's to the management place, and you have to be able to do it both in oral and written form. And even though you hate it, you got to be able to present your work. It's one of the critical steps that we have to do. All right, I'm going to open up for questions. I've told some good stories today, but I'm going to open up for questions. Guys, yeah. Over Enid.
I had a question about the dart design. I was looking at it and I noticed that the front of it, it looks as if, from what I can tell, about 1 centimeter of the nose of the airplane is cut off. Is that correct?
Now, 1 centimeter of the nose is what?
It looks as if it's either cut off or folded inside of itself.
It's folded inside because they didn't cut it.
Okay.
It's folded inside. They didn't cut it. That's on the standard design. Your design doesn't have to do that. Other questions? Everybody else awake this morning? Okay, there's a sign-in sheet around somewhere. Make sure that you get signed in. If you are turning in paper copies of something, make sure I get it. And then I'll see you guys next Tuesday.